So I'm Christos Cassandras, and I'm going to shift the emphasis of the discussion on smart cities.
Christos,
Yes.
actually I see the desk sharing, but I don't see the slides yet. There you go. I think now and if you can start that in a slideshow
It
mode.
says on my screen that you're sharing a screen.
I see them now, and I don't see them in slideshow mode.
I am in slideshow mode.
Okay, so maybe there's a bit of delay. Go ahead then.
Okay, can you see my first screen?
Yes.
Okay, all right. So as I was saying, I'm going to shift the emphasis of the discussion a little bit more towards the science and technology side. And that's why my presentation is entitled Smart Cities as Cyber Physical Systems. So I'm going to try to make the case for why, as engineers, we can tackle interesting problems in smart cities through the framework of cyber physical systems that we're familiar with. So this is, if you can see this picture, this is my view of what a smart city is as a dynamic system, a cyber physical system. As you can see, if we start at the top, our first task is to collect data from the city, and we can do that through the technology of sensor networks that by now is fairly mature. Once we collect the data, we process the data, and we translate the raw data into useful information, and this is where this whole revolution of big data and related technologies come about. Once you make this transformation into useful information, you make decisions, and then you close the loop, as shown, by taking the appropriate actions, such as controlling vehicles in a particular manner, or activating different distribution and allocation of energy, and so on. Of course, there are many, many related issues which makes this problem very complicated. I list some here: privacy, security, the management of energy in a wireless environment, and of course, safety. Now, if you look at this picture, let me make the case for why this is what we call a cyber physical system. In other words, a combination of both information-based and physical-based modeling and associated control and optimization methodologies. So on the right side, we can argue that this is really part of a cyber system. I have a picture of a model which shows something that we call an automaton. It might be a finite state machine, a Petrinet. There's all sorts of models that we're well aware of, and this has to do with the cyber side. But then, at the decision-making side, you're dealing with physical entities, whether it has to do with transportation or energy or the environment. You have to have models, as shown on the left there, which are the more conventional physical models that rely on differential or difference equations, and that's the physical side. Then, when you're communicating, again, now in the opposite direction, giving commands to actuate different physical devices, you're back in the cyber side. And then finally, you have to translate everything into physical action. So all of this creates what we call a cyber physical system. Now, why is this important from a technology standpoint? It's important because this is what in control science and systems engineering we call a hybrid system. It combines the models on the right, on the cyber side, with the models on the left, the physical side. And we know how to deal with these systems. Therefore, we can address many interesting problems. So in the rest of this presentation, my goal is to give you a sense of some of these problems that we can deal with. Before doing that, I want to address the word smart, because that's something that Carlo Alberto also mentioned. Everything is smart these days. So let me give you my interpretation of smart. I'm going to use the smart parking problem, something that I'll say a little bit more in a minute, as an example. So in a smart parking environment, what you do is you want to collect data, provide the data to a driver, and tell the driver where there might be a good parking spot for them. But notice on the picture on the right that once this information is given to the driver is pretty much left alone to find that parking space, if it's still available. And of course, we don't even know if it's really a good spot for him. So essentially, the message here is that collecting data is not smart by itself. It's a necessary condition for being smart. What's really smart is processing the data and closing the loop to make intelligent decisions. So in the picture on the right, I am trying to convey the idea that in a smart parking application, it's not just about providing drivers with data. It's about using this data to help the driver make the right decisions and perhaps in an automated self-driving car environment even do all of the action implementation by itself. So that's my interpretation of smart. So now we can talk about some applications by focusing mostly in the aspect of urban mobility. Carlo Alberto laid out the many different facets of a smart city, especially as we described and covered them in our special issue. And here I'm showing you a depiction of the smart parking application that we're working on. The idea is to find an optimal parking space for a driver, and I can explain what optimal is, and reserve it. So I'm going to give you kind of the highlights of some of these apps, and then, time permitting, I'll get you into a little bit more details. The second application has to do with electric vehicles, which have to be routed and recharged in different ways than the regular fossil fuel vehicles that dominate our transportation system nowadays. So not only do you have to have different considerations in making optimal routing decisions, but also you have to find the best charging stations and reserve space in those charging stations. So this makes for an interesting problem in an urban setting. Traffic control in general is a big problem. We all know that. It has to do with urbanization that the two previous speakers both emphasized. And we have a great opportunity here to exploit the connected vehicle technology, the automation, if you will, of driving, and also to take into consideration that gives us the opportunity to move from a selfish point of view that we all drive under today to a social point of view and seek optimal in a generic system sense way to the traffic problem. In the urban setting, we have a lot of traffic lights that we can actually adaptively control to both reduce congestion and benefit the environment. And again, if I have time, I'll talk a little bit more about that. Street bump is a very interesting, different kind of application that we're working on in Boston that has to do with detecting roadway obstacles, we call them bumps, and classify them and help the authorities in a smart city to allocate the resources in a prioritized way to take care of those bumps. And finally, returning to the theme of smart autonomous car, we have several projects ongoing. These are not just me, but many projects in which we're trying to basically integrate what we know about the powertrain, the engine of the system, and how we can give the powertrain information from the network side, from the vehicle dynamic side, how the vehicle perceives and interacts with its environment so as to automate cars.